So now we're going to discuss hypergeometric distributions. So this is another distribution. So before we had binomial distributions, and there were some conditions, and if we had those conditions, then it was a binomial distribution, and we could use a formula. So this is a different one, and this one's going to be called hypergeometric, not hypo, hypergeometric. And if we meet some conditions, then we're going to be able to use some formulas. So the conditions are actually pretty similar to the binomial. So repeated trials, we already did that. Two outcomes, which once again we're going to describe as success or failure. And the big difference is going to be, instead of the probabilities being independent, the probabilities are going to be dependent. In particular, we're going to have a situation where we have essentially a pool of items. And right, so we have a bunch of items in a bag, and we're pulling things, well, pool in this case, pool. We're removing things from the bag, and that's going to change the probabilities of, I should have actually done it. So we have a bunch of failures and successes in the bag, and pulling out a failure makes it less likely you're going to get a failure, and pulling out a success makes it less likely you're going to get a success. So if these three conditions are true, then it's hypergeometric. Let's have an example of a hypergeometric distribution. So we have here, a bag contains 14 marbles, 6 are green, 8 are red. You will draw 7 marbles from the bag without replacement. So it's multiple trials, we're pulling 7 things out. We have a pool of outcomes, we have 6 greens and 8 reds in a bag. And we're gonna say that, well, we'll see what the question is, but there's a good chance we're gonna be able to describe this as a success or failure. So it says A, but really, it's just one part. So what is the probability of pulling exactly 3 green marbles? And we've kind of done this already when we covered basic probability. So if you don't remember how to do this, you can go back to one of my probability videos. So what we have is let's use a different color for that. So what we have is 2, 3, 4, 5, 6, 7. We want to get exactly, so we're going to pull 7 marbles, and we want to get, what was it? Yeah, 7 marbles, those are those. We want to get 3 of them to be green. So 3 greens, and then the rest are going to be red. So how many ways are there of doing that? Well, of the 6 greens, we're choosing 3, so it's going to be 6 choose 3. Of the 8 reds, we're taking 4 of them, so it's going to be 8 choose 4. And then our NS, our total that we're doing this out of, is we're just picking 4 marbles. 7, 1, 2, 3, 4, 5, 6, 7, with no restrictions. And so that would be 14 choose 7. So the probability of getting what we want is going to be 6 choose 3 times 8 choose 4 over 14 choose 7. Okay, so what we're going to do now is we're going to try to turn that into a formula. So before we turn to a formula, we're going to do a small note on notation. So the book uses one set of letters, but I use a different set of letters. If you want to use the book set of letters, that's fine. Truthfully, when I do these problems, I don't even use this formula. I just work it out. But we're going to do this anyway. So I say, here, I should cover these up. I say that N is the number of trials. A is going to be the number of outcomes in the pool that we're going to call a success. T is going to be the total outcomes available in the pool. And X is going to be the number of successes that we're looking for. I like this one because N still means number of trials, and T kind of means total. It all sounds good. The book, and presumably official lettering, it changes number of trials to R, and it makes A, and then it says the total outcomes in the pool are N, but X is still X. So I'm gonna do this assuming this lettering, but if you want to do this lettering, that is your prerogative. Okay, so let's figure out the formula. I need these things over here. So what we know is n was the number of trials. So the number of trials in this case was 7. We pulled out 7 marbles. A is the number of outcomes in the pool that are a success. So we're saying that greens are successes, and there were 6 of them in the pool, so A is going to be 6. There was a total of 14 marbles available in the pool, 6 plus 8. So the total was 14. And the question we were looking at, we wanted to have 3 green marbles. So that's going to be 3. So putting that over there, putting it all together, and that was our calculation. We did 6 choose 3 times 8 choose 4 over 14 choose 7. So it looks like the 6 is the A, choose X. The 8 comes from the total minus the successes. We're basically counting the number of failures. So it's going to be T minus A. Choose, and the 4 comes from we wanted 3 successes, so the rest have to be failures. So N minus X. All over 14 is T, and 7 is N. And that'd be the formula. And I kind of pre-wrote it nicely. I guess that wasn't really necessary. So this is the formula. This is the probability of getting X successes if there is a hypergeometric distribution. So we don't need this. We don't need this. Let's do one quick example. So what we have is full deck of cards, 10 cards are drawn. What's the probability that exactly 4 will be hearts? So we'll kind of do the same thing we did with binomial. We're going to write success. We're going to write down all our letters. N, A, T, and X. So what we're going to call success, we want exactly 4 to be hearts, so we're going to say that, and remember success is for 1 trial, so it's going to be that we draw a heart, or we pull a heart out of the deck, not draw a heart. N is the number of trials, we're pulling 10 cards out, so that's going to be 10. A is the number of things that are successes in the pool, so the pool is 52 things. Well, actually, we should jump over to there. There's 52 things in the deck. Of those, how many of them are hearts? 13 of them are hearts. And we're looking for 4 successes. That's it. So putting that all together, the probability that X is 4, that the number of successes equals 4, is going to be 13 choose 4 times 52 minus 13 choose 10 minus 4 all over 52 choose 10. Or to put it another way, 13 choose 4 times 39 choose 6 all divided by 52 choose 10. Which I think works out to, I calculated this before, 14.7%.